In the last lecture, we talked about probabilities related to flipping coins and rolling dice. In statistics, though, the main situation involving probability is going to be picking random people from a population. So we'll be interested in probabilities like, if I pick a random person from this population, what's the probability that I get someone who likes Netflix? So today we'll talk about probabilities related to picking random people. What we have here is called a contingency table, or a two-way table, and it's usually used in situations where we're collecting two pieces of data, and most of the time it's two pieces of qualitative data. Here, we're asking people, what city do you live in? Sacramento, San Francisco, Los Angeles. And then we're also asking people, what's your favorite mode of transportation? Car, train, plane. The numbers here are frequencies. They're counting how many people. For instance, this 12 means that there are 12 people who are from Sacramento, and at the same time, they said plane was their favorite mode of transportation. This 5 means that there's 5 people from San Francisco who said car was their favorite mode of transportation. Part A. If one person is selected, find a probability that the person prefers travel by plane. In symbols, what I'm looking for here is probability, that's P, of getting someone who said plane was their favorite. And the way you read that is probability of plane. And how do we find probability? Remember from last time, the bottom number is going to be the number of things in our sample space. So here we're picking a random person, so we don't know who is going to be picked. But we can talk about the sample space, which is just a list of everybody that could be picked. And what I care about for the bottom here is really just the number of people. So how many different people can I pick from? In other words, how many different people are there in my sample? And the way you find out is just add up all the frequencies. So adding up all the frequencies, 6 plus 15 plus 12, plus 9, or plus 5, plus 9, plus 15, plus 0, plus 6, plus 17. 85 people total. So there's 85 different people that I can pick from. That's going to be the bottom. For the top, how many people said plane was their favorite? So these 12 people said plane. Also, these 15 people said plane also. And these 17 people also said plane. So 12 plus 15 plus 17. 44. Part B. If one person is selected, find a probability that the person's favorite mode of transportation is not by car. In symbols, I'm looking for the probability of getting someone who is not car. The bottom, how many different people can I pick from? That's going to be the total, 85. And for the top, how many people are not car? Well, here are the car people. Not car would be all the train people together with all the plane people. Okay, so all the train together with all the plane people. So 15, 9, and 6. 15 plus 9 plus 6, that takes care of my train people. Plus 12 plus 15 plus 17, that takes care of my plane people. So together, that is 74. Now, the next two parts involve some keywords that I want you to pay attention to. Part C says, if one person is selected, find a probability that the person is from Los Angeles and prefers travel by plane. Part D says, find a probability that the person is from San Francisco or prefers travel by train. So in probability, the word and the word or means something very specific. So pay attention to those words if you see them. Part C. So I want probability that the person is from Los Angeles and prefers travel by plane. In symbols, what I'm looking for here is probability of Los Angeles, so LA, and plane. Bottom, still the same. Total number of people I can pick from, that's going to be 85. Now in probability, the word and means I want the people who are Los Angeles and at the same time Plain. So they need to satisfy both of those requirements at the same time. So how many people are from Los Angeles and at the same time like Plain? That'll be these 17 people. So these 17 people are from Los Angeles and at the same time they said Plain was their favorite. 17. And as a tip, when you're looking for and probabilities, it should just be a single number in your table. All right, next, part D. We're looking for a probability that the person is from San Francisco or prefers travel by train. So in symbols, I'm looking for probability of San Francisco, SF, or. Bottom, still the same. How many different people can I pick from total? That's going to be 85. Now, the word or in probability means I want the people that satisfies one of these requirements or both, right? They don't have to satisfy both at the same time. They just have to satisfy one of these. So how many people are San Francisco or train? Well, all the San Francisco people will count because they would satisfy the San Francisco requirement. And then all the train people would also count. Because they would satisfy the train requirement. So basically, I'm just taking all my San Francisco numbers and then combining it together with all the train numbers. And then when you add these things up, be careful not to count the 9 twice. So the way I usually do this is I'll just take all my San Francisco numbers first, which would be the 5, the 9, and 15. And then I'm going to add on the train numbers, but I'm not going to include the number that I already counted when I counted the San Francisco numbers. So for the train numbers, I just need to add on the 15 and the 6. Because the 9 I already got when I did the San Francisco numbers. So the new numbers will be the 15 and the 6. Okay, the bottom's 85. The top, let's add those up. 5 plus 9 plus 15 plus 15 plus 6. 50. Conditional probability. This is the symbol for conditional probability, and the way to read that is probability of A the line stands for the word given, that B already occurred. Another way to think about this is probability of A given additional information B. And once again, this line here stands for the word given. So anytime you see the word given in a question, it's asking for conditional probability. Part E. If one person is selected, find a probability that the person prefers travel by car, given that the person is from San Francisco. So keyword I see here is given, which means I'm looking for a conditional probability. So in symbols, what I'm looking for here is probability of car, given, so the symbol for given is vertical line, San Francisco. I'm looking for a probability of car, given San Francisco. So how do we find conditional probability? So what this is telling me is that I'm looking for a probability that the person prefers travel by car, but I'm given additional information that for sure this person is from San Francisco. So because I have this additional information that the person is from San Francisco, I can narrow down my table to just the San Francisco numbers. In other words, the given part, which is the second part, is telling me just to focus on the San Francisco numbers. When I count for the top and the bottom. So focusing just on the San Francisco numbers for the bottom, what's the total? So focusing just on the San Francisco numbers, what is the total? So 5 plus 9 plus 15. $29. So that's my bottom. Okay, for the top, still focusing just on the San Francisco numbers, how many like car? So focusing just on the SF numbers, how many like car? 5. Let's try another one. Part F. If one person is selected, find a probability that the person is from San Francisco, given, once again, I see the word given, that the person prefers travel by car. In symbols, what I'm looking for here is probability of San Francisco, given, that's the line, car. Okay, anytime you have conditional probability, you should narrow down your table or just focus on one part of the table. So this one is SF given car, so the given part, which is the second part, is telling me to focus just on the car numbers. For the top and the bottom of my fraction. So starting with the bottom, so focusing just on the car numbers, what is the total? Just on the car numbers, that's the 6, the 5, the 0, what is the total? Pretty sure that's 11. And then for the top, focusing just on the car numbers, how many are SF? So still focusing just on the car numbers, how many are SF? 5. Notice that part E and F are asking two things very similar, right? E is car given SF. F is SF given car. The only difference is the order. So what I want to point out here is that the order does matter, okay? Car given SF is different answer than SF given car. So be careful about the order. Let's try one more. If one person is selected, find a probability that the person is from Los Angeles, given that the person prefers travel by train. Once again, I see the word given, which means I'm looking for a conditional probability. And in symbols, I'm looking for Los Angeles, so LA, given, that's the line, train. Okay, anytime you have conditional probability, it's telling you to focus on a part of the table. So what should I focus on here? The LA numbers or the train numbers? It's always going to be the given part, which is the second part. So this is telling me I need to focus on the train numbers. So whatever is coming after the word given is what you should focus on. So here, given, train. Focus just on the train numbers. Okay, for the bottom, focusing just on the train numbers, how many are there total? Just the train numbers. The total would be 15, 9, 6. 15 plus 9 plus 6. That's 30. For the top, still focusing on train numbers, how many are LA? So focusing just on the train numbers, how many are LA? 6. As a tip, if you don't see the word given, then we're talking about regular probability like on the front page. And regular probability, the bottom is going to be the total of everybody. If you do see the word given, that means that we're talking about conditional probability, which means we have to focus on a certain part of the table, which means the bottom is not going to be the total of everybody anymore. Everything we've talked about so far has said if one person is selected. If one person, is selected. One person, one person. On this page, we're now asking if 2 people are selected, if 3 people are selected. So how do we find probabilities when we're selecting more than one person? We could think of selecting more than one person in steps. So selecting 3 people is the same as selecting one person, and then selecting a second person, and then selecting a third person. So how do we find that type of probability? We need the multiplication rule. So the multiplication rule tells us how to find that type of probability. It says the probability of A and then B. So selecting one person and then selecting a second person is the probability of A times, that's where the name multiplication comes from, the probability of B given that A already occurred. So let's see how we can use this formula. Part H says if 2 people are randomly selected, what's the probability that the first person prefers travel by plane and the second person also prefers travel by plane? Talk about 2 people, so 2 people we could think of as selecting the first person and then selecting the second person. And what this is saying is that the answer is going to be 2 probabilities multiplied together. So 2 fractions multiplied together. 2 fractions multiplied together. And let me make a note of what the first person is and what the second person is. First person prefers travel by plane. So I want the first person to be plane and the second person to also prefer travel by plane. So second person is also plane. And then we're just going to find the probabilities of each fraction of each person separately. First person. What's the probability that the first person prefers travel by plane? For the bottom, that's just going to be everybody. So the total, 85. For the top, how many people prefer travel by plane? Plane would be these 12, these 15, and these 17. So 12 plus 15 plus 17. 44. Okay, that takes care of the first fraction, the P of A. Now, this part, P of B, given that A already occurred. So what that says is, for any fraction after the first fraction, we have to take into account what's been selected already for the first, before that. So for the second fraction, because I already selected one person already for the first lot, I don't have the full 85 people anymore, right? I already picked one person already, which means I should be down to a total of 84 now. Okay, that's because I already picked one person for that first slot. Now, I want the second person to also be plane. So plane would be 12, 15, 17. Again, so we said that was 44. And then we have to ask ourselves, have we used any plane people yet? And the answer is yes, right? That first person was the plane person, which means I have to reduce by 1 because I already used one plane person already. So I don't have the full 44 anymore here. I'm down to by 1 to 43. Let's try another one, part I. If 2 people are randomly selected, okay, that means I need 2 fractions. What's the probability that the first person is a person from LA who prefers travel by train? So first person is LA train. And the second person is from San Francisco. So second person is San Francisco. Okay, we'll find the two fractions separately. First fraction, what's the probability of getting a person who is LA train? The bottom is going to be everybody, which is 85. The top, how many people are LA train? So how many people are from LA and at the same time like train? LA train, 6. Now, any fraction after the first fraction, we have to take into account what was picked before that. Okay. For the second fraction, the bottom, because we already picked one person already, we don't have the full 85 anymore. We're down to 84 for the bottom. For the top, San Francisco. San Francisco, right, it doesn't state car, train, or plane, so just general San Francisco would be 5, 9, 15. So 5 plus 9 plus 15 is 29. Is it 29, or do I have to reduce like I did in part H? And you should ask yourself, have we used any San Francisco numbers yet? No, we have not. Because the first person was LA, so we haven't used any San Francisco numbers yet, so we don't have to reduce. So for the San Francisco number, the second fraction here, we should have the full 29. Right? Because we haven't used any San Francisco numbers in the first slot yet, so we have the full 29. In part H, we had to reduce by 1 because we did use a plane number already in that first slot, so we had to reduce by 1. J, if 3 people are randomly selected, so 3 people, 3 fractions. What's the probability that the first person is a person from San Francisco who prefers travel by plane? So first person is going to be San Francisco plane. SF plane. Second person is a person from Los Angeles who prefers travel by plane. Second person is LA plane. And the third person prefers travel by plane. So third person is just plane in general. Okay, we'll find the 3 fractions separately. First person, what's the probability of getting a person who is from San Francisco and prefers travel by plane? So San Francisco plane. Bottom is going to be everybody. So everybody is the total, 85. And then how many are SF plane? SF plane, 15. Second fraction, for the bottom, keeping in mind that we already selected one person for that first slot. We don't have the full 85 anymore. We should be down to 84. For the top, so how many people are LA plane? So LA plane, 17. And the question is it 17 or do we have to reduce to 16? And the question you should ask yourself is, have we used any LA planes yet? We have not, right? We used SF plane, but we haven't used any LA planes yet. So LA plane is this 17, right? We used, for the first lot, it was SF plane. So we used somebody from that box. We haven't used anybody from the 17 box yet. So we should have the full 17 for that second fraction. And then the third fraction, for the bottom, once again, we don't have the full 85 anymore. We actually used 2 people already. So we should be down to 83 people now, total. For the top, plane. So it doesn't state a city. So plane just means plane in general. So 12, 15, 17. That's 15 plus 17. And that's 44. So let me write that out here. Okay, question is, have we used any plane numbers yet? Yes, we have, right? First person was plane, second person was plane. So actually we've used 2 plane numbers already, which means we have to reduce by 2. So it's not going to be 44. Reduce by 2, it'd be 42. And that's because we've already used 2 plane people already. So we don't have the full 44 anymore. We're down to 42. Right? We had to reduce by 2. So make sure you understand why that's 42 and not 44. Part K. If 3 people are selected, so 3 people, that would be 3 fractions. What's the probability that the first person is a person from Sacramento who prefers travel by car? The first one is Sacramento car, so Sac car. The second person is a person from San Francisco who prefers travel by train. San Francisco train. And the third person prefers travel by car. So the third person is just car. First fraction, the bottom's going to be the total, everybody, 85. And then how many people are Sac car? So Sacramento car. Sacramento car, 6. For the second fraction, keep in mind that we already selected one person, so we don't have the full 85. We're down to 84. SF train. SF train. SF train, 9. Okay, question is it 9 or do we have to reduce? Question you should ask is, have you used any SF train yet? You haven't, right? First person was Sac car. So we haven't used any SF train yet. So we should have the full 9. Third fraction, for the bottom, keep in mind that we already used 2 people, right? So we don't have the full 85 anymore. We're actually down to 83 now. For the top, car. So car in general, it doesn't state the city, so car in general would be 6, 5, and 0. Okay, 6, 5, and 0. I don't need a calculator. 6, 5, and 0 is 11. And you should ask yourself, have you used any cars yet? And how many? First person was car. Second person was train. So we've used 1 car, which means we have to reduce by 1 to 10. Okay, so make sure you understand why it's 10 and not 11. And make sure you also understand why in part J, we had to reduce by 2, and in part K, we reduced by 1. In J, right, we used 2 planes already in the first 2 slots, so we had to reduce by 2. In K, we only used 1 car in the first 2 slots, so we had to reduce by 1. Okay, so let me now talk about probabilities that involve the words at least 1. And before I do that, I have to introduce this idea of a complement. And let me do that using an example. Say E stands for it rains today. The complement of E and the symbol for complement is going to be E with a little c. The complement of E is it does not rain today. So just stick on the word not, and that's the complement. So what's the relationship between the probability of E and the probability of its complement? Say we know that the probability of it raining today is, I'm just going to pick a random number here, 0.20, which as a percent is 20%. So say we know that the probability of it raining today is 20%. What's the probability of the complement? What's the probability that it does not rain today? If we know that the probability of it raining today is 20%, the probability of it not raining is the rest of the percent, which is 80%. And so what math did we do to get this 80%? 100% minus 20% is 80%. Okay, so that's using percents. If we're using decimals, right, instead of doing 100 minus, we just use the decimal version of 100%, which is 1. So in the decimal version, we would have done 1 minus 0.20. And we would get 0.80, which is the decimal version of 80%. So the point I want to make here is that if you know one of these, if you do 1 minus, that will get you the other one. Okay, so I'll write that out here. So the probability of E is 1 minus the probability of the complement. And then the other way around, the probability of the complement is 1 minus the probability of regular E. And all that's really saying in fancy math language is that if you know one of these, do 1 minus, and that will get you the other one. Okay? All right, so now we can talk about at least one problems. So let me jump to part L here. So it says if 3 people are randomly selected, find a probability that at least one person is from Sacramento. So keywords on this page are the words at least one. Now, what does at least one mean? At least one means one or more. So I have 3 people, probability that at least one or more is from Sacramento. So doing this directly is hard. And it's hard because at least one can mean a lot of things, right? 3 people, at least one from Sac could mean one person is from Sacramento. It could mean 2 people are from Sacramento. It could mean 3 people are from Sacramento. And even worse, within the 1 people from Sacramento, it could mean the first person is from Sacramento and the other 2 are not. It could mean the second person is from Sacramento, other 2 are not. It could mean the third person is from Sacramento, other 2 are not. Within the 2 people, there's many possibilities there also. So if we're going to do this directly, we would have to find the probabilities of each one of those situations separately and then combine them. Right? Too much. That's hard. The idea here is instead of finding at least one directly, we'll find a complement and then just do 1 minus it to get the probability that we want. So now the question is, what is the complement of at least one? So what is the complement of at least one? And let me use an example to illustrate. So I'm going to write down some numbers. Which of those numbers would count as at least one? So if I say at least one, which numbers would be at least one? At least one means one or more. Which numbers are one or more? One or more would be the 1, the 2, the 3, the 4, the 5. Right? All of those numbers that I underlined would count as at least one. Okay. What is the complement of at least one? So what is the complement? So what number is not underlined? So that's complement. Remember, complement means not. So what number is not underlined? 0. So the point here is that the complement of at least one is 0. Complement of at least one, and instead of 0, I'm going to write none here. And that's going to be our strategy. So to find probability of at least one, we're going to do 1 minus the complement, which is none. Okay, and that's the strategy we're going to use for any problems that involve the words at least one. So let's see how to do this with an example. Part L, if 3 people are randomly selected, find a probability that at least one person is from Sacramento. So I'm looking for at least one Sac. Okay, at least one Sac. Doing it directly is hard because there's too many possibilities. Idea here is we're going to do 1 minus the complement, which is none from Sac. Okay, at least one Sac is going to be the same thing as 1 minus none from Sac. Let me elaborate on why this is actually better. We already said earlier that doing at least one Sac directly was hard because it involves too many different possibilities. 8 to be exact. The complement of at least one, none from Sac, is going to be easier because there's only one way that you can get none from Sac. So if I have 3 people, none from Sac, the only way that I can get none from Sac is to have all 3 be not Sac, not Sac, not Sac. So one possibility versus 8. So our answer is going to be 1 minus. I want the probability that none of these people are from SAC. And we're talking about 3 people, which means I'll need 3 fractions. And so 3 people, none of them from SAC, means that I want not SAC, not SAC, not SAC. Right? That's what it means for 3 people, none of them from SAC. Okay, first fraction. Let me find my table. For the bottom, how many people total? 85. For the top, how many people are not Sacramento? Not Sacramento would be the San Francisco together with the LA numbers. So 5, 9, 15. 5 plus 9 plus 15 plus 0 plus 6 plus 17. 52. Second fraction, I also want to be not SAC. So the bottom, keeping in mind that we picked one person already. So for the total, we're down to 84 because we can't pick that person again. For the top, I also want to be not SAC. So not SAC, the total was 52, but because I already have one not SAC already, I have to reduce that down to 51. For the third person, I also want to be not SAC. At the bottom, right, because we already picked 2 people, we have to reduce by 1 again to 83. And then the same thing for the top. I also want to be not SAC. And because I already chose 2 not SAC already, I have to reduce now again to now 50. And your final answer is going to be 1 minus 52 over 85 times 51 over 84 times 50 over 83. Don't forget the 1 minus. M. If 2 people are randomly selected, find a probability that at least one person prefers travel by train. Keyword is the word at least one. Anytime you're looking for something with at least one, the idea here is 1 minus none. So the setup, I'm looking for at least one train. Instead of finding it directly, the idea is we're going to find a complement, so 1 minus none. So at least one train, complement would be none train. And then I want to do 1 minus. How many fractions do I need? We're talking about 2 people, so 2 fractions. So 2 people, I want none of them to be train. So that means I want not train, not train. First fraction, the bottom is going to be the total, which is 85. Up top, I want how many not train. So not train would be the cars together with the planes. So 6 plus 5 plus 0 plus 12 plus 15 plus 17. 55. Second fraction, for the bottom, because I already picked one person, I have to reduce by 1 to 84. And then second person, I also want to be not train, which means the top, I have to reduce by 1 to now 54. So final answer will be 1 minus 55 over 85 times 54 over 84. Okay, notice that on both of these, I'm looking for at least one SAC, but because we're finding the answer using the complement, when I do my fractions, I want not SAC, not SAC, not SAC, right? I'm looking for at least one train, but because I'm using the complement for my fractions, I'm looking for not train, right? Don't forget the nots. Part N. If 3 people are randomly selected, find a probability that all 3 prefer travel by plane. So when I read that, did you hear the words at least one? No. Okay. So if you see at least one, your final answer will be 1 minus some fractions. If you don't see the word at least one, then you should do it the same way we did it on a previous page. So I didn't see the word at least one. This is 3 people. So my answer should just involve 3 fractions, okay, without the 1 minus. 3 fractions, I want all 3 prefer travel by plane. So I want all 3 to be plane, plane, plane. First fraction, the bottom is going to be the total, 85. Up top, how many like plane? 12, 15, 17. So 12 plus 15 plus 17, 44. Second fraction, on the bottom, because I already picked one person, for the total, I should be down to 84. And then for the same reason, for the third fraction, on the bottom, I should be down to 83. Up top, I want to be a plane person. I already picked a plane person, so I should be down to 43. And then for the same reason, for the third fraction, I should be down again to 42. We talked about a lot of stuff today. We talked about the difference between ands and ors. We talked about conditional probability, which are the ones that have the words given in them. We talked about picking multiple people, and then we also talked about probabilities that involve the words at least one. And we talked about all of that in the context of a contingency table and picking people. So now I want to talk about all of those things in the context of a dice. So part A, if a 20-sided die is rolled, what's the probability of getting a number bigger than 8 or a multiple of 6? So when I roll this dice, let me list out the sample space. So when I roll this dice, what are all the different numbers I can get? This is a 20-sided dice, which means I can get 1, 2, 3, 4, all the way up to 20. And let me list that out. And in this problem, I'm interested in numbers that are bigger than 8, and then also numbers that are multiples of 6s. So bigger than 8, let me put circles around those. So which numbers are bigger than 8? Bigger than 8 are 9, 10, 11, 12, 13, 14, 15, 16. Okay, those are the numbers bigger than 8. And then I also care about multiples of 6s in this problem. So which numbers are multiples of 6s? Multiple of 6 just means count by 6s. So 6 is one of them. Plus 6, that will get you to 12. That's another one. Plus 6 again, that will get you to 18. Okay, so I'm putting boxes around my multiples of 6s. Okay, numbers bigger than 6 or bigger than 8 are my circles. Numbers that are multiples of 6 are my boxes. And now I can answer all these questions. Part A is looking for bigger than 8 or multiple of 6. So in symbols, I'm looking for bigger than 8 or multiple of 6. Okay, so keyword here is the word or. The bottom is just how many different numbers can I get? How many different numbers can I get? So 1 through 20, there's 20 of them. And then the word or. The word or means I want the numbers that satisfy at least one of these requirements. So numbers that either have a circle or a box or both. So basically I'm looking for all the numbers that have something marked on them, either a box or a circle. And I don't want to count things twice. So I don't want to count to 12 twice. I don't want to count to 18 twice. So I'm just going to count everything that has something red on it. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, that's OR. So I'm taking all the circled ones, all the boxed ones, combining them, but making sure that I don't count the 12 twice and I don't count the 18 twice. So there's 13 of them. Part B, if a 20-sided die is rolled, what's the probability of getting a number bigger than 8 and a multiple of 6? So I want bigger than 8 and multiple of 6. Okay, bottom's going to be how many different numbers can I get total? There's 20 of them. And then the word and means I want numbers that satisfy both of these requirements at the same time. Bigger than 8 are my circles, multiple of 6 are my boxes. I want the numbers that have both a circle and a box on them at the same time. How many are there? That would be the 12, has a circle and a box. 18 has both a circle and a box on it. There's only 2 of those. Part C, if a 20-sided die is rolled, what's the probability of getting a number bigger than 8 given, so keyword here is given, that the number is a multiple of 6. So this is a conditional probability. So in symbols, I want bigger than 8. Given, which is the line, multiple of 6. So anytime you have a conditional probability, you have to focus on certain numbers. And you're going to focus on the given part, which is the second part, or in the sentence, anything that comes after the word given. So given, multiple of 6. We're going to focus just on the multiples of 6. For the top and the bottom. So for the bottom first, focusing just on the multiples of 6, how many are there total? The multiples of 6 are my boxes. So focusing just on the boxes, how many are there total? 3. And then for the top, still focusing on just the multiples of 6s, how many are bigger than 8? So focusing just on the multiples of 6s, how many of those are bigger than 8? 2, the 12 and 18. Part D, if a 20-sided die is rolled, what's the probability of getting a multiple of 6 given that the number is bigger than 8? Okay, once again, I see the word given. Okay, that means this is a conditional probability. In symbols, I'm looking for multiple of 6 given, which is the line, bigger than 8. Okay, anytime you have conditional probability, you're going to focus on certain numbers. What are we focusing on here? We're focusing on anything that comes after the word given. So given, bigger than 8. Or if you have it in symbols, is the second thing. So I'm going to focus on just the numbers bigger than 8. For the top and the bottom. So focusing just on the numbers bigger than 8, how many are there total? Bigger than 8 are my circles, so focusing just on my circles. How many are there total? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then still focusing just on my bigger than 8s, how many of them are multiples of 6s? So my bigger than 8s are the circles, so focusing just on the circles, how many of those are multiples of 6s, which are the boxes? Focusing just on the circles, how many of those are boxed? Just 2. Part E, if 2 20-sided dice are rolled, what's the probability that both are bigger than 8? Okay, so now we're talking about 2, right? Everything else was talking about 1 dice. Now we're talking about 2 dice, similar to picking 2 people. I need 2 fractions. And then multiply together. First one, I want to be bigger than 8. both bigger than 8, so the second one is also bigger than 8. Okay, first fraction, the bottom, how many different numbers can I pick total? 20. Top, how many of them are bigger than 8? Bigger than 8 will be the circles. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Second fraction. So this is where dice differ from picking people. So when I pick people, remember I said for the second fraction, we have to keep in mind that we already picked one person for the first fraction. So implicit when we're picking people, I don't want to pick the same people for the first and second slot, right? Which is why whoever I picked for the first slot, I'm not going to pick for the second slot, which is why we had to reduce the total by 1. For dice though, whatever happens on the first dice, right here it's 11, that is, I can still get an 11 on the second dice, if I can find it. Right, so whatever happens on the first dice, for the second dice, because it's a separate dice, I should still have the full 20 for the second dice. So unlike picking people, for dice, we're not going to reduce. Because whatever happens on the first dice, second dice is almost like a reset, and we can have the full 20 to choose from for the second dice. Second dice, bigger than 8, bigger than 8. Circles, 12, don't have to reduce because we're talking about dice. Part F, if two 20-sided dice are rolled, so 2 dice, 2 fractions, what's the probability that the first row is bigger than 8 and the second row is a multiple of 6? First one, I want to be bigger than 8. Second one, multiple of 6. First fraction, the bottom, how many different numbers can I get total? 20. First fraction up top, how many are bigger than 8? Bigger than 8 are the circles. I think we counted 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Second fraction, because we're talking about dice, we don't have to reduce. The bottom is still going to be 20 again. Up top, how many are multiples of 6? Multiples of 6 are my boxes. 3. Part G. If two 20-sided dice are rolled, what's the probability that at least one number is a multiple of 6? Okay, keyword I see here is at least 1. So anytime you have an at least 1 probability, the idea here is to do 1 minus none. So I want at least 1 that's a multiple of 6. But the strategy is, instead of doing that directly, we're going to do 1 minus the complement, which is none, multiple of 6. Okay, 1 minus. How many fractions do I need? We're talking about 2 dice, 2 fractions. And then what does it mean for none of them to be multiple of 6? So none of them multiple of 6 means I want not multiple of 6, not multiple of 6 for both of them. Okay, so even though we're looking for at least one multiple of 6, because we're getting the answer using the complement, for the fractions we want not. So not multiple of 6, not multiple of 6. Okay, first fraction, the bottom, how many different numbers can I get? Same as all the other ones, 20. And then how many of them are not multiple of 6? My multiples of 6s are the boxes. Okay, so how many of them don't have a box on them? How many of them don't have a box? So don't have a box would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 17 numbers there that don't have a box on them. Second fraction, because we're talking about dice, we don't have to reduce. So the bottom is still going to be 20. Up top, I also want that to be not multiple of 6. And because we're talking about dice, you don't have to reduce. It should still be 17. All right, so that's it for today. Have a great day. See you next time.